Okay. Now, so 1.7 is called functions. Because they're fun. Yay. I know, said no one ever. I get it. It's fine, guys. Okay, let's talk about what a function is if we don't remember. So let's define it. Function is a type of relation. Is a relation. Which is why we had to learn them first. In which each element in the domain is paired with exactly one, underline those words, exactly one element of the range. That's its math term wordy definition. Star form, what this really means is, break it down for you, that domain, right, means what letter, X or Y? X, right? That means each X value can never, I'm capitalizing this, repeat. That's it. That's what that really means. So if you have a bunch of points, right, or order pairs, that's what they mean. You cannot have any of them that have the same X value. That's all that means. If so, it is not a function. It's just a relation. Okay, it's just part of some kind of equation. That is all that means. So what we're going to do is we're going to look at every form of a relation, look at its information, and see if it's just a relation or if it's actually a function. Okay, so we're going to see if it's just specific or if it's just a general thing. Okay, let's start with the easy one. We'll work our way up. Example 1, let's start with a table. My table is going to be sideways though. X on top, Y on the bottom. I'm going to say them as ordered pairs. First order pair is 1 and 4. 1 comma 4. Second order pair is 3 comma 2. Third is 5 comma 4. Fourth and last is 1 comma negative 4. Instructions say determine whether each relation is a function, period. Explain. So you have to say yes or no, it is a function or isn't a function. And then you have to say why, no matter what. So again, starred sentence says each X value can never repeat. So only thing we care about are the X values. Look at the X values. Ignore the Y's. They're not even important. Do any of my X values repeat? Yes. So is it a function? No. So I'm going to write this is not a function. That's my first part. Then it says, right, I have to say yes or no. I did. Explain. How do I explain? What did you see that tells you no? Because the value, the X value, 1 is used twice or is repeated. However you would like to say that. As long as you say that something is used twice and be specific, ta-da, you're done. Pretty easy. Tables are easy. Order pairs are easy. Hard one, maps. Let's look at a map. Now, these ones, we label them as domain and range, which is okay. As long as you remember that domain means X and range means Y, you're fine. I'm going to make them as rectangles too because my ovals never turn out well. So my rectangles aren't doing too hot either, so it's fine. It's fine, guys. Okay, in my domain, this is the values I have. -2, 0, 3, and 4. In my range, I have the values -3, +6, and +9. Maps are all about the lines, aren't they? So right now we don't know anything. So we got to see our lines. First line, -2 to -3. Second line, 0 to 6. Third line, 3 to 6. Fourth line, 4 to 9. Now, again, maps are all about the lines. Again, we only care if the x's are repeated. So again, look at it. Are any of my x values used more than once? No. How do you tell if it's used more than once? What would you see? What do you mean? Well, you can't see numbers actually repeat because in maps we don't actually have numbers repeating. Yes. In maps, you'd have one number and two lines coming from it. Like if you look at the range spot, you see how that 6 has 2 lines coming from it? That is a repeat, but since it's in my range, do I care about it? No. So we're only looking over here. Do these numbers have any 2 lines coming from them? No. Since there's not 2 lines coming from this, is this a function? Yes. So this is a function. Again, if it says explain, if you have to explain, what would we say? You can literally say there are no domain values repeated or no x values repeated. Or every domain value used only once. It depends on how wordy you're really feeling. Okay. Okay. Next, a couple vocabulary words for you. We have discrete functions. I'm going to talk about another one right after this. So a discrete function is a function, obviously, based on its name, with points that are not connected. Like everything you did yesterday. Graphs with just points all over them, right? Like a scatter plot, right? Remember scatter plots with just a bunch of points over them? There's no lines, just points. That's a discrete function. Then a continuous function this is just some vocabulary for you to learn. What do you think this guy is? Yes, a function, it's got a little specifics to it. A function graphed with, ooh, I almost spelled that wrong. That's sad. An unbroken line or curve, because we do curves in this one, period. So continuous function has no breaks whatsoever. Just important to know that in this class, we're going to talk about all kinds of graphs, straight lines, and curvy ones. In algebra, we like curves. Okay? Okie dokie. Next, do we remember what this means? The vertical line test. Do you remember what that means? What does it mean? Correct, which is good because we haven't looked at this type of relation we haven't looked at, right? Is graphs. That's why, because we need to remember what the vertical line test was, right? The vertical line test is only used for graphs, whether they're discrete or continuous. And you don't really have to write the definition if you remember what it is, right? So just important to remember. You also call it the pencil test. Oh, geez Louise. Come on. Wake up. Thank you. So you use it. You can either draw a straight line. You can use your pencil or your marker, or you can, yes, use a piece of paper or a ruler. I do have rulers in the front of the room. Whatever going on, as long as it's straight, right? To see if that picture or those points cross that line more than once, which is what we're about to do. Because we're going to look at some curvy things that confuse some people. Okay? For example, let's start with an easy one. Okay? Number 1. You do not have to draw these very big. I would just do like maybe at most 4 lines, 2 up top, 2 on bottom. You get what I'm saying? Okay, let's just start with the basics. If I put a dot there, and a dot there, and a dot over there. I tried to make them fixed so you can see where my dots were. Is that a function? All you have to say is yes or no. You do not have to say why in this one. All you have to do is write yes or no underneath it. Now, if I ask you why, you're most likely wrong. A little hint for future reference. Is it yes or no? What do we think? It is yes. It is a function, right? I tried to make them as far apart as you could tell. It's kind of hard from the projector to you copying down my picture, isn't it? Okay, so this one, big old yes. Okay, try another one. This one's going to be an actual picture with some lines in it. How about, I should use 2 colors. Wouldn't that be smart? This guy. I don't know why I've been doing this for all day, and I just thought of using 2 colors. Vertical line test. Remember, draw a line. Think of the vertical line test. Why? It's one picture. It's not 2 separate points. It's one big picture. It's a V. It makes a graph. It's just like that picture over there between Cass and Lila on the cabinet. That's a graph. It's called an absolute value graph. We're going to learn a lot about it. The real question is, it's a graph, but is it a function? Yes, ma'am. It is. Thank you for playing, though. Okay, number 3. What if I take that graph and I just rotate him? Definitely not, right? If I draw a line right here, definitely crosses that picture twice, doesn't he? Doesn't matter where I draw that line. Okay. Example 4. This is always the one that gets people. And I should have used colors earlier. I have to draw it in 2 pieces or it never looks pretty. It is one picture. If that does not look sufficient to your liking, there is a picture directly above Lila's head. There's even a grid there. What'd you think, Jimbo? What'd you say? It is a function. Who also thinks it is a function? It is a function. You are correct. It slowly gets wider and wider, and it is all connected to make one function, which is fine. So it's still continuous, right? These 3 are continuous functions. I'm just putting up the lid on that, and this is a discrete function. Okay? This is the hardest. Ready? Last one. How about this guy? Open circles up there. Closed circles on that one. The top one has an open circle on it. Bottom one has a closed circle on it. Think about this one. This one's been throwing people all day. I haven't had any arguments yet, but usually I always get arguments. Maybe it'll be today. I like when you argue with me. So, anyone want to take a guess and tell me why, no matter what, if you're right or wrong? AJ, what you thinking over there? Why are you thinking no? It looks right to you, so you said no? That doesn't even make any sense. Lila? You haven't talked to me all day. What you thinking? That's not an answer. You think it's a function or you don't think it's a function? You don't think it's a function? What's telling you no, it's not a function? When your mind's going, this can't be a function. Try. It's honors. I like to challenge. They're both in the same spot. That's true. That's true. Is there a difference? Could there be a difference between an open dot and a closed dot? Let's think about it. Let's visualize it. I wish, oh, I can do it underneath the camera. You can look at me. It's much more fun. A closed dot means I have something, right? It's in my hand. An open dot, if I had an open dot, that thing in my hand goes right through. So an open dot doesn't actually take up that space because it's open. It doesn't cover that spot, like that spot. So you have an open dot and a closed dot together. If they overlapped, this one's open. So it's only actually hitting that spot how many times? Once. It like slides it right in. If my hands were big enough, it would work. So is there more than one dot hitting the same spot of X? No. This is a function because of the open dot, closed dot. If they were both closed, you could for sure say no. No. If they were both open, you could still say yes. Because open means that they have nothing, there's nothing going on there at all. The only thing that would stop it is two closed dots. Also, if there was randomly, because this does happen, like throw you off, if they randomly decided to put a dot like right there for funsies, then over here, there would be two things in the same spot. Okay, so that one is a tricky one. Also, what kind of function is discrete or continuous? It is disconnected. A discrete function is not all the way connected. A continuous function is unbroken, completely unbroken. You just always think discrete means a bunch of dots. It doesn't. Discrete means not fully connected, not connected at all. Are these not connected in one way? That's enough information for them. Continuous, it's all or nothing. Discrete, all kinds of answers. It's like saying you're blonde. And there are like 52 shades of being blonde. Right? Same thing. Okay. Now, let's talk about, we looked at the picture. Let's talk about equations. Because they're going to ask you if something is a function, and they're just going to give you this. I said, is this a function? And you're like, oh crap. What did I learn in middle school about lines? So this is my cheat sheet because we actually haven't talked about it because that's what chapter 2's for, okay? If you have a x and a y, they have the same power, and they are just there together, it makes a solid line, a diagonal solid line. Does a diagonal solid line, no matter what form, pass the vertical line test? Yes. So all functions in this form, for now, because we haven't learned the specifics, are a function. All lines are a function for now. That's when we have both variables. Now we got to talk about when we only have one variable. Like, hey, y equals 2. That's all we have. That's our entire equation. Really, I should write an example next to these, right? It's a 6 and that's 7. Okay. So now you have to think about it. If you don't know something, think about what it looks like visually. So, got a little graph. We know that our x-axis is left to right. Our y-axis is up and down, yeah? Where is y equals 2? If I was going to plot that point, where is y equals 2 if I start here at my origin? I'm going to go up 2, and it would be a point somewhere right there, right? Just, just guessing because I didn't even make tallies, right? We're just guessing, right, AJ? So, I have a question for you. If I stay here, but just scoot over a little bit, does y still equal 2? Yes. If I stay there, but then just scoot to the left or right, does y still equal 2 that way? Yes. So a y equation by itself makes the picture of a horizontal line. Because y equals 2 left to right. No matter what x is, y is 2. So then you go back to what Dana said. Well, does this pass the vertical line test? It does. Yes, ma'am. For sure. I guess. So y, he's really the ringleader in this. So then let's think about x. X equals, how about -2 this time, just to make funsies. Okay, in my head, I'm not thinking it, so let's just look at it. Again, we know what our y-axis is, we know what our x-axis is. If I start at my origin, where is x equal -2? To the left 2, right? Just guessing. Now, where else does x equal 2 other than that spot? If I go right or left, I'm thinking different values of x, right? So now I'm going up or down. The way to remember it, if it helps, is your graph is always opposite of its axes. Now this time, what kind of line is that? A vertical line. Can a vertical line pass the vertical line test? No, because there's a bunch of x answers on that, isn't there? So this answer, no. Okay? So the other part of your homework, it'll give you equations and they won't give you the picture. So either you have to imagine the picture or just know. If it's just y equals, it's always yes. If it's just x equals, it's no. If they're together and equal, it's always yes. Okay? Now, combining like terms does not count. If you had y equals 2x plus 3 plus y, are they still the same power? The powers are still the same on your y's and on your x's? Then it's still yes, because they're still the same power. Okay? But we'll get into that later. Okay. Next part, I just see how much room I had, is function notation. I'm not going to fit this all on one board, sadly. So an equation, just backing up for a second, looks like this. I'm just making an example of y equals 2x plus 3. That's an equation. I just made it up. It could be anything I want it to be. That's really crooked. then a function of this format, wake back up, come on, looks like this. F parentheses, x parentheses equals 2x plus 3. What is the only difference between the equation and the function? This says y equals, this says f parentheses of x parentheses, right? They're exactly the same thing. Well, here's a fun fact. Y is the same thing as f parentheses of x. They are actually the same thing. They're interchangeable as long as something's a function. Also, how you say this, f of x. That's how you say that. A function of x, or f of whatever's on the inside. Okay, so if you see f of x, that means they're telling you it is a function. You don't have to guess. Then we're going to find function values. So it says for this, and they'll give you a function, f of x equals negative 4x minus, oh, no, plus 7. I'll add you, plus 7. Find each value, and it gives you a bunch of questions. First one, f of 2. So in the parentheses, instead of x, what do we got? 2. So we replaced x with 2. So what are you going to think we're going to do in the equation? Replace x with 2. When you plug something into an equation, what should you put around it? Please. So you just put negative 4 parentheses, 2 parentheses, plus 7. Type that in, or please do it in your head. I hope you can. When you do function notation, and I am very picky about this, you should always write your answer f of 2 or whatever they're asking you for equals and then the answer. You shouldn't just write 1 and then circle it, which is not 1. It's close though. So don't just write, hey, x equals 5, because that's not how this works. You have to write the whole thing. All right, that's how we did that before. Are you about to pee your pants? Ah. Did we all get negative 1? Okay. So what if I say f of a? What do you think? What are we doing? Still. You always save the smart comments. What do you do with the thing that's in the parentheses? What did we do with the 2? Plugged it in. 4x. What are we going to do with the a? Plug it in. It's a variable though, right? We can't actually solve things with variables. So when you plug variables in, especially when they're by themselves, you just basically change the variable, and that's going to be your answer. So now it's negative 4a plus 7. There's no math because there was no actual number. Right? So if we keep that, you can fill out your thing if you'd like to go to the bathroom. Okay. If you keep that, that's why I left it up there, and I say find f of negative 4y, that changes the whole game. Now you're not just plugging in y, you have negative 4y to plug in, yes? So you actually have some simplification to do. But anytime there's a variable in there, that means there's going to be usually more than one term in your answer. So all you're going to have to do is plug negative 4y in for x, and will we have some math? A little bit, just a little bit. What operation we had to use up there? What's going on? With the negative 4s? Multiplication. What's that turn into? What's my final answer? 16y plus 7, because the beautiful negatives, they just cancel out. And since 16y and 7, can I add those together? Why not? Which is called what? What's that called when I can't add them together? They're not what? Like terms. Gold star for Dana. Okay. Try something a little harder. How about f of a plus 5, close your parentheses. Oh, what's going on here? What are you plugging in for x? All of it in parentheses, yes? Which means you're going to have to use what math property? What's this? Right here. I'll give you a sticker if you know the answer. Distributive property, yes, thank you. It's not that hard. Come on. Don't be afraid. I'm really not that scary. That's because I've already eaten by now. I'm usually less angry by now. So then, this one you distribute. 7 doesn't have anything to do. Now, AJ, can I do anything with what I got? What can I do? I can combine my like terms. I was hoping you would use the vocabulary. And take 20, negative 20 and 7, add them together because they're right next to each other. So negative 20 plus 7 is what? Negative 13. So negative 4a, he has no friends, he's just left alone, minus 13. Does that make sense? Crazy? What? No one saw that. I wrote 3 twice. Okay. What about when I don't have stuff inside the parentheses? What if I say f of 6, but then I say minus 5 afterwards? So that minus 5 is not inside the parentheses. What do you think that means? Huh? Oh, it matters. But what's the order of things we're going to do? We're going to do the f of 6 first. So f of 6, we're going to say, hey, let's do this math right here. Let's take 6 and plug it into that equation. So negative 4, plug 6 in, plus 7. Let's find that answer. Negative 4 plus times 6 plus 7. What's that answer? Anybody? Negative 17. Then, at the end, we're going to apply whatever was on the outside. So now what are we going to do? We're going to subtract 5. Well, since they're both negative, it makes the number bigger. Then what do you get? Negative 22, which is really close to the answer we started with. We'll put 5, 6 in before we subtracted 5, added 7. Right? That looks like a 7. It's not, it's a 2. And then I would write it up here with this to show that all of that equals negative 22. Yes? What about this one? We're not going to solve this. I'm just asking. Now let's change this variable. There you go. What does that mean? What are we doing? We're not going to solve it. I'm just asking. Some verbal confirmation. We're going to do this part first. You do the function part first. You take y and plug it in for all your x's, which you'd have an equation, right? So I'll just show it to you, right? So it'd be like negative 4y plus 7. Then what are we going to do with this? You bring it down. What operation is that? Distributive property, right? It's multiplication. You just multiply everything by 5, and that would be your answer, right? Do all the function stuff first, leave everything else up for last, right? That is 1.7. Does that make sense? It's not so bad. This is why we learn relations first. Okay. Flipping. Okay. Ooh, there's a back that's empty. I like it. Let's see what we get there. Okay, now 1.8 is interpreting graphs of functions. Okay, let's talk through some common sense knowledge. What's an x-intercept? I don't even have to write it down. I shouldn't have to anyway. What is an x-intercept? Whatever the graph is, the picture, now we're going to have actual arcs or curves or straight lines or whatever. They're mostly curves. It crosses the x-axis, yes? What's a y-intercept? Okay, right? So, duh. That's the kind of question you're asking me. Yeah, okay. What does it mean to have, this is a good one, a line of symmetry? For example, people have a line of symmetry. Humans, well, most humans, depending on what's going on. We have a line of symmetry. What does that mean? A graph, well, usually we're talking about graphs, right? Yes. So that means things are equal. We can cut it vertically. That's a big hint. Is it has to be cut vertically, graphs and humans. And it is equivalent or equal on both sides. So yes, you are correct, ma'am. So a line of symmetry, right? It says a graph has a line of symmetry, right? In the y-axis, usually, slash a vertical line. If each half of the graph on either side, I cannot spell, matches exactly. I did not make enough room. Period. Which is exactly what you just said. Okay. Now, ooh, colors are going to be great in this experience. Now, we're talking about what graphs looks like and their parts, basically, which sounds really weird if you think about it. Matches. Yeah, that was where I didn't have enough room to breathe or write or think. Oh, I'm scooted too, also just because you can't read it. So we're talking about parts of a graph. So I'm going to give you the same picture multiple times. We're just going to talk about what's going on. I'm going to give you this picture. It is going to look like a weird loop, that weird loop. I'm going to make the same picture multiple times. We're just going to talk about different things. Bless you. Threw away my red marker. What a day. Okay. First thing is we want to talk about when a graph is positive versus when a graph is negative. Okay? With this picture, I'm going to show it to you. When you look at it, it's based off of based off of the y values. So on the y-axis, where are the y values positive? This is not a trick question. It is really that easy. Where are the y values positive on the y-axis? above the x-axis. So in this picture, right, this is why we use colors, everything that's up here, right, everything in this section is positive, right? More specifically, from here to here and here to here, that's the only stuff that's positive, yes? And then the negative stuff is everything below, but more specifically, this loop is negative, and this little tail guy down here is negative. I apologize in advance for my lack of warning about the colors. Okay, so you're going to have to be able to write or draw a picture and show that something is positive or negative. Now, same picture. It gets more increasingly round every time I draw this, every year. I can't tell you why. Now we're going to talk about when something increases or decreases. This we should get. When we look left to right, you want to follow always left to right and say, where does this increase or decrease? So you always start here. If I start at this arrow, I'm going down, aren't I? So is that increasing or decreasing? Anybody? If I'm going down, I'm decreasing, right? Start up here, I'm decreasing. I used to use wiggly lines. Where do I stop decreasing? Yes, before you start to go back up, not before you hit the y-axis, because I'm already going up over here. It is always at the curve or the round of a curve at the middle, okay? Because right here, it's like I decided, I rolled down the hill, now I have to climb back up it. So I'm going down here, and then I'm like, oh, now I'm going to climb this hill, which means left to right. What am I doing? I'm increasing, right? Here, all the way to the middle of that hump, I guess that's backward, that mound. And then once you get back to the mound again, you're like, I'm going to roll. It's like one of those penguin games, remember we used to slide and hit the hills? That's what makes me think of. And then down here, I'm going to decrease again. Now on paper, you're going to have to like note all of this information. So I like to use colors because one, it's more pleasing to my eyeballs, and two, because it's less confusing than with a bunch of pencil and a bunch of different designs. Okay, this so far pretty easy. Okay, these things, these mounds, are called high or low points. In math, what do we call high and low points? Starts with an M. They both starts with M. A minimum and maximum, right? Oh, let's use this one because this one's more intense. What is this one called? Because it's the top one. What's this guy called? A maximum. And what do you think this guy's called? A minimum. Can I call something that's going on with an arrow a min or a max? No, because we don't know where it ends, correct? So a min or max, they call them relative min or relative max. I just call them min or max, right? So min or max are when they're the highest or lowest point in that area. So you'll also have to be able to label that. I'm going to touch my screen before it goes to sleep. And then the last thing is those arrows. We have to describe what they're doing. So this arrow, you follow the picture from the origin every time, left to right. What are my X's doing when I go towards this arrow? What are my X's doing? My X's are going towards increasing, right? Which is, I can write X increasing. Now think about them in the Y's term. The arrow's going down. What are my Y's doing? Yep, decreasing. Now do the other arrow. You always start at the middle and go towards that arrow. What are my X's doing this way? Yep, X is decreasing. What are my Y's doing? That is called end behavior. What is going on at the end? That's literally where it gets its name from, which hopefully makes sense. So what you're going to have to do is look at an image and, oh baby, I'll draw one for you. It won't be pretty. There you go. Here's an image. Sometimes they have numbers on them and they describe the X and the Y axis and do all that crazy stuff. That's unnecessary. Right? You're going to have to label all of these things. You're going to have to state. It says, identify if it's linear or nonlinear. So AKA, does it make a straight line or not a straight line? Completely, 100% a straight line. No. Okay, so it's nonlinear. Estimate the x-intercepts. I would just say on this one. On the other ones, they actually have numbers on them. So you'd say, oh, the x-intercept is kind of at 8 because they have numbers on them. This one, how many x-intercepts do I have? 3. How many y-intercepts do I have? Only 1. You usually only ever have 1. It says, is there any lines of symmetry? Could I cut this in half and make a perfect line of symmetry? Ooh. I'm going to say no because Miss Ronaldo drew it. Okay. Find where it's positive and negative. So then we go, okay, and you have to mark it. You can either use a color or a specific design. Okay, it's positive here with this wiggles and this wiggles. That's my positive. And I would note over here that this is my pause. And then I would do negative and mark the same thing and then say my negatives. Right? Then we say increasing or decreasing. So starting on the left, if we do increasing first, this is increasing all the way to that point, and that point makes it easier, right? Where else is it increasing? So we just stick with one color. All the way over here, right? From this point at the bottom, all the way up. And that middle line, from connecting those 2 points, she's decreasing. Does that make sense? Yes, no? Does this picture at all have a maximum other than it looks like Notre Dame threw up on it? Anybody? Does it have max or min points? Yeah, it has points, right? That are not arrows. This is your max up here. This is your min. Can we, because they have arrows, describe their end behavior? If they do not have arrows, if it's like a picture that starts here as a y-intercept and goes up, that is not an end behavior, okay? It has to have an arrow on the end to be an end behavior, okay? And you're going to have to try to draw these. I'm going to change. I thought you had a question. Okay. So you say x increasing or decreasing. So the first 5, 5 through 10, those are, they give you pictures, describe them. I would like put your paper over it and like trace the picture so you don't have to try to draw it again. And then I need what, 13 through 17? I will, you know what? I think 16 and 17 are easier. I'm just going to make you do 16 and 17. So 5 through 10 and then 16 and 17. I'll fix it online too. Because I think 13, I think these ones are harder. Now 16 and 17, it gives you information. It says like, hey, your x-intercept is 2. Your y-intercept is 5. Can you try to make a graph using that? And it'll tell you that something is increasing or decreasing. So it's you trying to go backwards. It's just practice. Okay? Tomorrow, we'll talk. I'm going to make you a review. And I'm honestly thinking that I usually make reviews. I don't know why I didn't schedule one. I usually give you a review day, and we do the review all during class, and then we take the test the next day. And I didn't schedule it for chapter 1. I have no idea why. But I would like to do that because you haven't had that. So I think tomorrow will be review day, and then your test will still be Monday. Just so that you have that. And that way it gives you a chance to feel this out on the computer. Because I think this is difficult on the computer. Where is my arrow and where is the stop button?